You ever stop to think how much of what we call reality is actually just our best guess? I mean, we're out there building telescopes like the James Webb, this $10 billion marvel designed to see the universe's baby pictures from, what, 13.8 billion years ago.
It's pretty wild when you phrase it like that.
Think about the sheer chutzpah. We're trying to measure the infinite with something we hammered together on Earth. And get this, it's 1.5 million kilometers away. If it hiccups, there's no cosmic tow truck.
Nope, no AAA out there.
It's all riding on theories we haven't even fully proven yet.
Yeah.
Welcome to the Deep Dive, where we take the stuff you've been reading, and boy, you've sent us some brain ticklers this time, and boil it down to the fascinating core. We're your guides, sifting through the mind-bending so you don't have to.
Doing the heavy lifting.
Today, we're plunging headfirst into this wild idea that our understanding of the universe isn't just passively observing what's out there, but actively inventing it.
Right, inventing it. It sounds controversial, but...
It's like we're not just reading a cosmic story, we're kind of co-writing it with our instruments and our ideas.
Yeah, that's a great way to put it.
We've got a cosmic roller coaster of thought ahead. We're going to zoom from the earliest stargazers to the cutting edge of modern cosmology, looking at how our tools and our hidden assumptions have shaped the universe we think we know.
Those hidden assumptions are key.
Expect some serious aha moments, and hopefully a few laughs along the way. We're here to make the complex captivating, just for you.
Hopefully.
And before we launch into this deep space of ideas, if you're digging what we're doing here and want to catch more dives into the fascinating, give that like button a click and subscribe. It helps us keep exploring these incredible topics together. Okay, let's untangle this cosmic yarn.
That opening really grabs you, doesn't it? This notion that science, which we often see as purely objective, this, neutral way of looking at things, actually has these incredibly deep, almost invisible roots.
Right, not just cold, hard facts.
Exactly. As the philosopher Emil Meyerson put it, metaphysics penetrates all science for the very simple reason that it is contained in its point of departure.
Wow, so it's baked in from the start.
Totally. Think of metaphysics as the unseen scaffolding, holding up the entire building of science, the fundamental beliefs about what reality is and how we can even begin to understand it. It's the stuff scientists usually don't even question, but it's always there, shaping the very questions they ask and how they interpret the answers.
So like the operating system running in the background that we don't even notice.
Kind of, yeah. So when we talk about metaphysics here, we're not drifting off into some abstract philosophical cloud. We're talking about the very edges of what modern physics can even touch, those unspoken assumptions, those principles we take for granted, the implications lurking beneath the surface of our theories that we can't directly test in a lab.
Okay.
These are the foundational ideas that actually make our experiments possible in the first place.
Gotcha. Like you have to assume something to even start experimenting.
Precisely. Consider this. The historical drive to find a single, unified law that governs the entire cosmos, expressed in elegant mathematical language. Where did that powerful idea come from?
Good question. Seems natural now, but maybe it wasn't always.
It wasn't just a random scientific hunch. It was deeply influenced by theology, by the ancient concept of a single creator, God, and a harmonious designed universe. Over centuries, this idea morphed into a metaphysical proposition at the heart of science.
Yeah.
The belief that such a unified mathematical language exists out there, waiting to be discovered.
So that belief in mathematical order wasn't just observed, it was sort of inherited.
You could say that. So before we even build a telescope, we're already operating with this ingrained belief that the universe speaks math, and we just need to learn the dialect.
Right. It's like we've got this cosmic Rosetta Stone in our minds, even before we find the actual inscriptions. Now, that brings us to this fascinating concept of a world object, and where something as colossal as the James Webb Space Telescope fits into that picture.
Yeah. This is where the philosopher Michel Serres offers a really cool way to think about it. He talks about a world object as a tool that's perfectly matched to revealing a specific dimension of reality.
Okay, like a key fitting a lock.
Exactly. Think of a satellite that lets us grasp the speed and scale of global communication. Or, as he says, an atomic bomb that reveals the immense power locked within matter. By this definition, the JWST is absolutely a new kind of world object.
Because it's built to grasp the universe's scale and history.
Precisely. Its entire design and purpose are aimed at expanding our reach into the deepest cosmic history and the very edges of the observable universe, pushing the boundaries of what we can even perceive about the cosmos' size and age.
But here's the really mind-bending part you mentioned earlier. It's not just taking pictures, right?
Right, exactly. And this is crucial. The JWST isn't like some super fancy digital camera just snapping photos of galaxies. It's way more complex and, in a way, more indirect than that. It's designed to collect data based on very specific, pre-programmed settings, focusing on particular wavelengths of light and predetermined areas of the sky. This raw data then has to be painstakingly reconstructed using incredibly complex algorithms and our existing theoretical frameworks to create the stunning images we eventually see.
So the image is a reconstruction, not a snapshot.
Bingo.
Yeah.
So even our most advanced and seemingly direct observations of the universe are actually filtered and shaped by the theories we already hold. We built a telescope based on our current understanding of cosmology, and then we interpret the data it sends back through that very same lens. It's like we've built this incredibly sophisticated ear to listen to the universe, but we've already decided what kind of music we expect to hear.
That's how.
It's a subtle but super important point about how science actually works. Our tools don't just show us reality. They actively participate in constructing it for us.
It's like we've spent billions to build this amazing keyhole to peek at the universe, but the shape of the keyhole itself dictates what we can see. And the stakes with this cosmic key are just astronomical, right? Pun intended, I guess.
Absolutely. Astronomical stakes indeed. The financial investment in the JWST is staggering. It ballooned from under $1 billion to around $10 billion.
$10 billion.
Yeah. That's a massive amount of resources that could have gone to countless other scientific endeavors, many of which were put on hold. And as you pointed out, the risks are immense, unlike the Hubble, which astronauts could repair. Well, the JWST is so far out in space that there's no plan B. It has to work flawlessly from the start.
That's nail-biting stuff.
Totally. And even the testing process highlights this constant back and forth between theory and experiment, because the fully assembled telescope was too enormous for any test chamber on Earth.
Right, you can't just stick it in a big fridge.
Exactly. They had to break it down into smaller pieces, test each part individually, and then rely on incredibly complex computer models to predict how the whole thing would behave in the harsh vacuum of space. As the project manager famously said, they weren't just testing the hardware, they were proving their ability to model reality accurately.
So testing the model as much as the machine.
Precisely. This
Right.
really shows how theory and experiment are in this constant dance, each informing and shaping the other.
Mm-hmm.
But beyond the technical challenges, there's also this deeper, more philosophical risk.
Mm-hmm.
What if our fundamental theories about the universe are just plain wrong?
Ooh, yeah.
What if, despite all our ingenuity and the incredible technology of the JWST, the basic assumptions underpinning our entire cosmology turn out to be flawed or even completely off base?
That would be devastating.
All that investment, all those hopes pinned on this one instrument could potentially lead to a scientific dead end, or at the very least force a radical and uncomfortable rethinking of everything we thought we knew. And with other major space telescopes aging out, a failure could leave a real blind spot in our view of the cosmos. Talk about pressure.
That's a terrifying thought. Spending all that brain power and billions of dollars only to realize we might have been asking the universe the wrong questions all along. And that leads us to this super intriguing area of the mathematical universe and some of the, well, the giant question marks lurking within it.
Exactly. It's when we dive into the numbers and the equations of cosmology that things start to get really weird and wonderful. You mentioned the Hubble constant earlier.
Right, the expansion rate.
Yeah. Our best measure of how fast the universe is expanding. Even tiny disagreements in how we measure this single number have led to billion-year differences in our calculations of the universe's age.
A billion years. That's not exactly pocket change.
Not at all. That shows you just how incredibly sensitive our cosmic models are to even small uncertainties. But what's perhaps even more mind-blowing are these concepts of dark matter and dark energy. Think about this. To make our current mathematical picture of the universe even remotely coherent, we have to assume the existence of these completely unknown substances and forces.
The stuff we can't see or detect directly.
Right. Supposedly making up about 95% of the entire cosmos. We have absolutely no direct empirical evidence for them. They are, in essence, theoretical placeholders in our equations, invented to make the math work.
95%. So basically everything we do see is just the tip of the iceberg.
According to the standard model, yeah. The icing on the cosmic cake, maybe?
Wow.
And this raises a really profound question about the very nature of scientific inquiry in this field. There seems to be this incredibly powerful drive to maintain a mathematically unified and consistent theory of the universe.
That elegance we talked about.
Exactly. And so the research then often becomes focused on finding evidence that confirms what the existing framework already predicts. It's a logic that, as the philosopher Björn Ekberg points out, can look suspiciously circular.
Right, like looking for your keys only under the streetlight because that's where the light is.
That's a perfect analogy. Are we building this elaborate mathematical castle in the sky and then just looking for building blocks that happen to fit the pre-designed structure?
It makes you wonder if we're sometimes more in love with the elegance of our equations than with the messy reality they're supposed to describe.
It's like we've decided the universe must speak math in a very specific dialect, and if we hear something that doesn't quite fit the grammar, we just invent new vocabulary or even new grammatical rules like dark energy to make it all work. That's a wild way to think about science.
It is pretty wild.
And it ties into this whole idea of science as an active invention and how much our historical and social context plays a role in what we consider to be scientific truth. We often imagine scientific knowledge as this objective mountain of facts just waiting to be discovered out there in the world. But thinkers like Bruno Latour and Isabel Stengers, who've actually studied how science is done in labs and research centers, what they call science in action.
Like anthropologists studying scientists.
Kind of, yeah. They offer a very different picture. They argue that scientific knowledge is, in a very real sense, a construction. It's not just a passive reflection of reality. It's an active process shaped by our historical moment, the specific tools and methods we happen to invent, and even the authority figures and institutions we rely on to validate it.
So it's not happening in a vacuum.
Not at all. Stengers has this really insightful idea that scientists are in the service of history, not just in the service of truth in some abstract, timeless sense. Their goal, she suggests, is to shape our understanding of the world in such a way that their inventions eventually come to be seen,
By everyone else.
both by their fellow scientists and by future historians, as inevitable discoveries that anyone could have stumbled upon. So the truth in this view becomes what successfully reshapes our collective historical understanding.
So convincing everyone it was obvious all along, even though it was an invention.
In a way, yeah, it's about convincing the world that what you've invented was actually always there, waiting to be found. And this leads to this fascinating concept they call the double constitution of an experimental event. It's not just about passively observing something that already exists independently of us.
Okay, break that down. Double constitution.
The very act of designing and conducting an experiment and then interpreting its results involves what Stengers calls the invention of the power to confer on things, the power of conferring on the experimenter, the power to speak in their name.
Whoa. Let that sink in.
Right. The experiment doesn't just reveal a pre-existing truth. It actively creates the conditions under which the experimenter can authoritatively claim to have discovered something new. It's like setting up a stage and then declaring that the play you've written is a true reflection of reality.
So the experiment gives the thing the power to give the scientist the power to talk for the thing.
You got it. That's the loop.
Okay, my brain hurts a little.
It's dense stuff. Stengers also describes this as reciprocal capture, particularly in the context of massive experiments like the Large Hadron Collider.
The LHC, yeah. Smashing particles together.
Right. Scientists have their theoretical predictions about what kinds of particles might emerge from these high-energy collisions, and then they sift through mountains of data, selectively focusing on events that seem to align with those predictions.
Confirmation bias, almost.
It's more complex, but there's an element of focusing attention based on expectation. They analyze these selected events, publish their findings, engage in intense debates with their peers, and through this whole complex social and intellectual process, the initial fleeting experimental event becomes retroactively constituted as a significant discovery.
So it becomes real through argument and agreement.
Essentially, yes. The more attention and even controversy it generates within the scientific community, the more solidified its status as a real finding becomes. It's like announcing, we found it, only after a long and winding road of interpretation and acceptance.
So it's not just about the raw data spewing out of the detectors. It's this whole intricate ecosystem of theory, experimental design, intense debate, and eventual acceptance that transforms a potential blip into established scientific knowledge. That's a far cry from the classic image of the lone genius in a lab having a sudden, solitary revelation. And it makes you wonder, how did these fundamental, often unspoken assumptions at the very heart of science even get established in the first place? What were the initial metaphysical building blocks?
To really grasp that, We need to journey back to the birth of modern science in the 17th century, with towering figures like Galileo Galilei and René Descartes.
The big guns.
Definitely. Galileo's invention and championing of the telescope wasn't just a technological leap forward, it was a profound metaphysical shift.
More than just seeing farther.
Oh, yeah. As the political philosopher Hannah Arendt astutely pointed out, it fundamentally altered our perspective, allowing us to conceive of and consider the Earth from the viewpoint of the cosmos. It was, in a very real sense, dispensing with the actual world to render a universe calculable.
Dispensing with the actual world. Wow, so prioritizing the measurable.
Precisely. By focusing on what could be measured and quantified through this new instrument, Galileo was intentionally setting aside the messy qualitative aspects of our everyday experience.
Then you have Descartes. I think, therefore I am.
Man himself. His philosophy laid the very foundation for what we now call modern epistemology, how we know what we know. His famous cogito, I think, therefore I am, established the individual thinking subject is the ultimate bedrock of all knowledge.
The mind becomes the starting point.
Exactly. He created this fundamental and enduring division between mind and body, between the realm of thought and the physical world, which became a cornerstone of Western philosophy and, by extension, of Western science. He essentially tried to locate that one unshakable point of certainty, what Archimedes sought not in the external world, but within the human mind itself, viewing mathematical formulas as the purest products of this thinking substance.
So math becomes the language of pure thought, separate from the messy world.
That was the idea. But there was another incredibly influential thinker at the time, Baruch Spinoza, the Dutch lens grinder and philosopher.
Spinoza, right. Often mentioned, but maybe less understood.
Perhaps. His perspective offers a really fascinating and often overlooked contrast to Descartes. Instead of focusing on the isolated cogito and the sharp separation of mind and body, Spinoza emphasized a radical logic of connection.
Connection, not separation.
Exactly. He saw everything in the universe, mind and matter alike, as interconnected expressions of a single fundamental substance, whether you choose to call it God or nature.
So no mind-body split.
Not in the same way. For Spinoza, all ideas, insofar as they are related to God, are true. He believed that belief itself wasn't something to be overcome on the path to knowledge. Rather, it was the initial spark, the fundamental affirmation that actually motivates our arguments and justifications.
Belief as the engine, not the obstacle. That's different.
Very different. So from this incredibly fertile intellectual period, these two distinct and powerful modes of thinking emerged, deeply shaping the very foundations of modern metaphysics.
Descartes versus Spinoza, in a way.
You could frame it like that. On one hand, you have Descartes with his emphasis on clear distinctions and the isolated thinking subject, leading to what we can call equivocal systems with a fundamental separation between a creator and the created world. On the other hand, you have Spinoza with his focus on interconnectedness and a single underlying substance, leading to univocal systems where everything is ultimately reducible to and understood through its relationship to this one principle.
Equivocal meaning multiple layers, univocal meaning one fundamental layer.
Roughly, yes. These two contrasting philosophical approaches continue to subtly influence how we think about the universe and our place within it to this very day.
It's like we had this major fork in the metaphysical road right at the beginning of modern science, and these two intellectual giants represent those diverging paths, both profoundly impacting how we even frame our fundamental questions about the cosmos. And how do these contrasting ideas influence something as seemingly straightforward as our understanding of motion?
That's a brilliant question, because Galileo's groundbreaking approach to dynamics was revolutionary, precisely because it involved what at the time seemed like a completely bizarre and even illogical move: the wholesale removal of the very medium in which bodies move.
He just ignored air resistance and friction.
Essentially, yes. He imagined this idealized, frictionless void to make the incredibly complex problem of motion amenable to mathematical analysis. It seemed to fly in the face of everyday experience after all. Everything we see moves through some kind of medium, whether it's air or water. But it was precisely this radical act of abstraction, this deliberate simplification of reality, that allowed for the mathematization of physics.
The math wouldn't work otherwise, basically.
Pretty much. Then came Isaac Newton with his monumental Principia Mathematica, building directly upon Galileo's work and offering this grand, unified framework of rational mechanics that could, at least in principle, explain the motion of everything in the universe in precise quantitative terms.
The clockwork universe idea starts here.
You could say the mathematical framework for it does. Newton himself saw his work as establishing the fundamental mathematical principles of all philosophy, moving methodically from observed motions to the underlying forces of nature, and then back again to explain and predict future motions.
But you mentioned a subtle shift.
Yeah, within this incredible development, there was a crucial and perhaps subtle shift. Traditional mechanics had somewhat separate areas of inquiry: kinematics, describing motion; statics, dealing with equilibrium; and dynamics, understanding forces in motion.
Okay.
Galileo, in a sense, found his way into dynamics through kinematics, by first focusing on mathematically describing motion itself, even if it meant initially setting aside the messy and complex forces that cause it. This kinematic approach became the essential foundation for Newton's grand synthesis, but it inherently involved this initial move of bracketing, of temporarily removing the real-world conditions.
So describe first, explain the cause later.
In a way. Yeah. Later, in the late 18th century, the mathematician and astronomer Joseph Louis Lagrange took Galileo's initial abstraction even further, pushing it into a purely mathematical realm. He generalized the concepts of equivalence and equilibrium, essentially redefining motion.
How?
Not as a continuous process driven by forces, but as a series of successive states of equilibrium. This was an incredibly powerful and elegant mathematical formulation, but it also carried with it the potential to fundamentally disconnect cause and effect.
Disconnect cause and effect. How?
If every moment in the motion of a body is just a static state of equilibrium, defined solely by its spatial configuration at that instant, what then actually drives the change from one static moment to the next? It becomes almost like an endless sequence of frozen snapshots, potentially erasing the dynamic singularity and the causal agency of actual motion.
So, by focusing so intently on the mathematical description, we might inadvertently be losing sight of the underlying why of things, the actual causal relationships that drive the universe. It's like we have this incredibly beautiful and precise equation that perfectly describes a dance, but in our focus on the equation, we've somehow forgotten the actual dancers themselves and the energy that propels their movements.
That's a really evocative way to put it. Yeah.
And around the same period, we also see the rise of probability and statistical reasoning, which feels like a whole other layer of complexity being introduced into our understanding of the world.
You're absolutely right. The 17th century wasn't just the age of mechanics. It also saw the significant emergence of probability reasoning, with key figures like Christian Huygens and Blaise Pascal laying the early groundwork.
Pascal's wager and all that.
Related ideas, yes. What's particularly fascinating is that right from its beginnings, probability had this inherently two-faced nature. On one side, it was deeply statistical, concerned with understanding the seemingly random behavior of large numbers of events, like the outcomes of games of chance.
Dice rolls, coin flips.
Exactly. But on the other side, it was also fundamentally epistemological, focused on how we assess reasonable degrees of belief in situations where we lack complete certainty and where statistical data might not even be available.
So chance versus belief.
Right. And philosophers have wrestled with the relationship between these two aspects of probability for centuries. Are they fundamentally distinct ways of thinking, or is one simply a special case or a more developed form of the other?
Does it matter?
Well, the historian of science Ian Hacking has suggested that there might be some deeper, almost hidden forces at play here, that something intrinsic to the very concept of probability resists being neatly divided into these two categories. Perhaps it's because even when we try to analyze probability purely logically and mathematically, we often implicitly refer back to a sense of a positive given reality, what we might call the autological.
The actual stuff happened.
The actual tangible world that exists independently of our calculations, even as we try to circumscribe or even exclude it in our abstract frameworks.
Okay.
Interestingly, while probability and statistical methods took off in various fields, from insurance to political arithmetic, physics, with its strong early emphasis on deterministic, mechanistic explanations, was initially slower to fully embrace them.
Because Newton's laws were supposed to be deterministic.
Exactly. Newton's dynamics, as we discussed, initially involved deliberately bracketing this autological given, the messy reality of forces, friction, and the media through which motion occurs. But as physics progressed in the 18th and 19th centuries, particularly as it began to seriously explore phenomena like light, heat, and energy, the very stuff of the world.
Right, the messy stuff.
Physicists increasingly encountered discrepancies between their idealized universal dynamical framework and the actual, often unpredictable conditions they observed in their experiments. It's in this context, in trying to grapple with these imponderables and the growing gap between theory and observation, that statistical reasoning gradually began to creep into the realm of physics.
So statistics became a way to handle the parts the deterministic laws couldn't quite capture.
That's a good way to think about its entry point, yes. Now, in the face of this growing tension between idealized mathematical descriptions and the messy complexity of the real world, the philosopher Henri Bergson offered a really compelling and rather unique perspective with his concept of pure perception.
Bergson. Sounds familiar. What's pure perception?
He asked us to try to imagine our immediate experience of the world as an unlimited fullness of images, a direct, intuitive grasp of reality that exists outside of our conscious minds.
Like unfiltered reality.
Kind of. This is a move reminiscent of Spinoza, suggesting a single, unified reality that is expressed in two fundamental systems of images. The universe itself, where these images interact causally and dynamically, and our individual perception of the universe, which is limited and filtered through the specific lens of our physical body, our body being itself a privileged image located at the center of this vast interconnected web.
So we're an image within a bigger web of images.
That's Bergson's idea. He argued that modern science often falls into a fundamental trap of ontological bifurcation, creating artificial and ultimately misleading divisions between subject and object, between mind and body, and between our internal experience and the external world.
Like Descartes' split again.
Exactly. This then inevitably leads to seemingly unsolvable epistemological problems about how these supposedly separate realms can possibly interact, and how we can gain reliable knowledge of a world that is fundamentally distinct from our own minds. He saw his concept of pure perception as a way to overcome these self-imposed divisions, emphasizing the inherent interconnectedness of subject and object as simply different functions within this broader field of interacting images.
Okay.
He critiqued modern science for its tendency to solidify and artificially divide the continuous flowing nature of reality in order to create stable points for practical action, potentially losing sight of the fundamental dynamism and interconnectedness of the real.
So Bergson was, in a way, pushing back against this increasing trend towards separation and abstraction in science, trying to keep us anchored in a more holistic and interconnected view of reality. But then, as the 20th century dawned, everything seemed to explode with the radical upheaval of the quantum revolution. How did that seismic shift shake up these long-standing assumptions?
Oh, the quantum revolution was truly a cataclysm for classical physics, a fundamental shattering of its core assumptions. The discovery of entirely new experimental phenomena like X-rays, radioactivity, and the perplexing behavior of electrons completely baffled the existing framework.
Things just stopped making sense according to the old rules.
Completely. Max Planck's invention of the quantum, initially just a mathematical trick, really, to explain the observed spectrum of black-body radiation.
Just a fudge factor.
It started that way, but it unintentionally laid the very foundation for an entirely new kind of physics grounded in discontinuity, in these discrete, indivisible packets of energy. It was a radical departure from the continuous waves and fields of classical physics.
No more smooth flows, just jumps.
Right. Albert Einstein, in his groundbreaking papers of 1905, famously took Planck's idea a giant leap further, reinterpreting light energy not just as being emitted and absorbed in discrete quanta, but as actually consisting of discontinuously distributed packets of energy, what we now call photons.
So light is particles, not just waves.
Or, weirdly, both. This was a profound link between Planck's somewhat formal metalogical approach, the mathematical rules that seemed to work, and a new understanding of the ontological reality of light itself, what light actually is. It was a truly revolutionary idea with far-reaching consequences.
And then the electron itself was found.
And then came the experimental discovery of the electron in a vacuum. This was a landmark moment, confirming the existence of a fundamental subatomic particle. But it also subtly highlighted a certain inherent circularity in particle physics.
What circularity?
A particle must, in a sense, be assumed to exist in order to design an experiment capable of detecting it. And conversely, we need this successful experiment to definitively demonstrate the particle's existence. It's a delicate dance between theoretical expectation and experimental verification.
You need the theory to build the detector, and the detector to prove the theory.
Precisely. The subsequent development of the electron microscope is a fascinating example of this interplay. It's a kind of third-order invention that cleverly exploits the bizarre wave-particle duality of electrons to break through the fundamental resolution limits of traditional optical microscopes.
Using the weirdness to see better.
Exactly. It's a paradoxical tool, using both the wave-like and particle-like behavior of electrons to allow us to see things that were previously invisible to us.
Okay.
Ultimately, the modern concept of a fundamental particle has become what we might call metalogical. It's considered real and meaningful, not necessarily because we can directly observe it in some classical billiard ball sense, but because it's an incredibly useful and consistent component of our theoretical frameworks.
Real, because it works in the math.
Pretty much. We can build elaborate theories with it, design increasingly sophisticated experiments based on its predicted properties, and even create more of these particles in high-energy accelerators. In a sense, probability, the statistical nature of quantum events, ends up begetting particularity, the seeming existence of discrete particles, which in turn begets a proliferation of new particles as our theories become more refined.
So the math leads to more particles being invented or found.
It provides the framework where they can be found and made meaningful. This fundamentally new way of thinking about the basic building blocks of reality also provided a completely new foundation for cosmology, for understanding the very early universe.
So the quantum revolution wasn't just about discovering tinier and tinier bits of matter. It was about fundamentally reshaping how we even think about the nature of reality itself and the very process of scientific inquiry. And this brings us to the invention of scientific cosmology and the rise of the Big Bang Theory. How did this particular narrative of the universe's origin story come to be so dominant? Was it just a straightforward accumulation of irrefutable evidence?
Well, as we touched on earlier with the James Webb and the Herschel Space Observatories, our understanding of the cosmos relies incredibly heavily on having pre-existing theoretical frameworks to interpret the vast amounts of data we collect.
Right, the frameworks shape what we see.
Exactly. Raw images of distant galaxies, for example, don't inherently tell us their age or their distance without a complex map of cosmological understanding, a pre-existing idea of what we're even looking for. And in a field like cosmology, where direct experimental falsification of fundamental theories is incredibly difficult, if not impossible, due to the immense scales of space and time involved.
Can't exactly rerun the Big Bang in a lab.
Not quite. So there's always this inherent risk of a certain kind of circularity. We build a telescope based on a particular cosmological theory, and then we look for evidence within the data it provides that seems to confirm that very same theory.
Finding what you expect to find.
It can lean that way. The philosopher Björn Ekeberg makes a compelling argument that the Big Bang hypothesis didn't achieve its widespread acceptance solely due to an overwhelming mountain of purely empirical evidence.
Ah, so what else was involved?
Instead, he suggests that it was remarkably effective at gathering and mobilizing interest and resources within the scientific community. It provided a compelling narrative framework that could accommodate a few fundamental observational constraints that other models struggled with. It became incredibly instrumental for guiding further research and for securing funding, and in that sense, it almost willed itself into becoming the dominant paradigm.
So it was useful, and that made it true in a practical sense.
It became the framework everyone worked within. Here, the political theorist Hannah Arendt's idea about how hypotheses can gradually become axiomatic, taken as self-evident truths through consistent action and belief, is really insightful.
Like if everyone acts like it's true, it sort of becomes true.
In terms of being the foundation, yes. What starts as just one possible explanation, in need of rigorous proof, can, through persistent effort, widespread adoption, and the construction of an entire research program around it, create a world where that initial assumption becomes the unquestioned foundation for further inquiry.
Like the calendar example you gave earlier.
Exactly. Think about something like our calendar year starting in January. There's no inherent natural or scientific reason for that particular starting point. It's a historical and cultural construct that we've collectively made true through consistent practice and agreement. The Big Bang Theory, in a somewhat analogous way, became the fundamental origin story upon which the vast majority of our scientific understanding of the universe is now built.
Okay, so it became the bedrock.
Ekeberg introduces the term hypology to describe this process. The act of positing something as fundamentally under itself as a foundational framework that is effectively established retroactively. To understand, in this context, then becomes the act of actively participating in and operating within that pre-established ordering idea.
Understanding means working within the accepted understory.
You got it. We understand January as the first month because we participate in the cultural and practical systems that make it so. Similarly, the Big Bang became the underlying framework, the under, within which almost all cosmological research now proceeds.
Got it. And Einstein's theories played a big role here too, right?
Absolutely. Einstein's revolutionary theory of special relativity was a crucial stepping stone. He fundamentally challenged the long-held Newtonian concepts of absolute space and absolute time, famously introducing the interconnected concept of space-time and the primacy of events within it.
Space and time aren't separate anymore.
Nope. Interestingly, his theory even relied on the hypothetical concept of a perfect vacuum as a kind of metaphysical prerequisite. Then, with his theory of general relativity, the very nature of gravity was reimagined, not as a force acting through space, but as a fundamental geometrical property of space-time itself, matter, and energy warping the fabric of reality.
Gravity is geometry. Still blows my mind.
Mine too. However, the project of unifying quantum mechanics, which governs the very small, with general relativity, which describes the very large, has proven to be incredibly difficult, perhaps the biggest unsolved problem in modern physics.
The theory of everything is still missing.
Still missing. There are fundamental differences in their very approaches to reality, what Ekberg again refers to as metalogical versus hypological. For example, they treat fundamental constants like Planck's constant h and Newton's gravitational constant g and the speed of light in profoundly different ways.
Okay, so they don't even agree on the basic constants.
They interpret their role and nature differently, which makes unification tricky. The Big Bang theory itself has its direct roots in nuclear physics, essentially envisioning the very early universe as the ultimate particle accelerator.
Hot, dense soup of particles.
Exactly. A super hot, super dense environment where fundamental particles were constantly interacting. Its prominence grew significantly alongside the increased funding and research focus on nuclear physics in the mid-20th century.
Ah, funding follows the physics, or physics follows the funding?
A bit of both, probably. Pioneering work by Stephen Hawking and Roger Penrose even applied the concept of singularities from general relativity to the universe as a whole, with the Big Bang being framed as an absolute alpha point, a beginning predicted by the equations of general relativity.
The singularity at the start.
Right. Of course, the Big Bang model has faced numerous challenges and has undergone significant modifications over time, such as the introduction of the concept of cosmic inflation.
That super fast expansion right at the beginning.
Yeah, a period of extremely rapid expansion in the very early universe, which has itself faced ongoing debates about its testability and the nature of its evidence. This highlights the evolving and sometimes shifting goalpost of what even counts as a rigorous scientific proof in cosmology.
The rules keep changing a bit.
Sometimes seems that way. Then there's the rather ironic reintroduction of something akin to Einstein's discarded cosmological constant in the form of dark energy to account for the observed accelerating expansion of the universe.
So the thing Einstein called his biggest blunder came back.
In a new guise, yes, to make the current observations fit the model. The emergence of the entropic principle, the idea that the universe appears to be fine-tuned for the existence of life, because if it weren't, we wouldn't be here to observe it.
We're here because we can be here.
Essentially.
Yeah.
That can even be seen as a way to account for our particular perspective as observers within this vast cosmos, effectively completing a kind of hypological circle between human and nature within the overarching framework of mathematical universality.
It all comes back to us being able to observe it.
In that view, yes. But all of this raises a profound and perhaps uncomfortable question. In our relentless pursuit of a single unified mathematical theory of the entire cosmos, are we potentially blinding ourselves to other equally valid ways of understanding the universe and our place within its grand tapestry?
The math goggles might be too strong.
Could be. Is the Big Bang theory, with its deep-seated faith in a fundamental underlying mathematical order, a mathesis universalis, perhaps a modern incarnation of a kind of theological or metaphysical conviction, a belief system dressed up in the language of modern physics?
Ooh, controversial thought. Science is faith.
Ekberg ultimately suggests that the universe, as presented by scientific cosmology, can sometimes appear as a somewhat hollow hypological construction, a semblance of unity and coherence imposed onto a far messier and more complex reality.
Wow. This deep dive has truly taken us on an incredible journey, from the very philosophical bedrock of science to the absolute cutting edge of cosmological research, and the overwhelming takeaway is this mind-blowing idea That so much of what we understand as the universe might be less of a passive observation and far more of an active invention than we ever could have imagined.
It really challenges the straightforward view, doesn't it?
It really does. We've seen how our fundamental tools, the powerful theories we construct, and these incredibly deep-seated and often unspoken metaphysical assumptions have collectively shaped our cosmic narrative in profound and sometimes surprising ways.
The whole interplay is fascinating.
It's not just about pointing our instruments outwards. It's fundamentally about what we ourselves bring to that act of looking, the invisible frameworks that color our interpretation.
The lens matters as much as what's viewed.
This really makes you stop and think, doesn't it? If our understanding of the universe is, in a very real sense, a construction, what are the inherent limitations of that construction, and what entirely new possibilities might that perspective open up for future exploration?
Big questions.
How does this shift in perspective change the way we even think about the nature of scientific truth itself?
Yeah. What does truth even mean in this context?
And that leaves us with this final, perhaps slightly unsettling thought. Could our very human drive to find a single, elegant, and unified mathematical theory to explain everything ultimately be leading us down a particular intellectual path, perhaps even blinding us to other equally valid and insightful ways of engaging with and understanding the vast and mysterious cosmos and our own unique and fleeting place within its grand expanse?
Are we missing other universes of understanding by focusing only on the mathematical one? Heavy stuff.
It's definitely something to keep pondering long after this deep dive is over. Thank you so much for taking this incredibly mind-bending journey with us.
My pleasure. It's been thought-provoking.
It's been a truly fascinating exploration, and we're already buzzing with anticipation for where our next deep dive into the realms of knowledge will take us. Until then, keep questioning, keep exploring, and keep that mind wide open.